Hi, welcome to this section on general graphing techniques. In this section, we're going to learn some tricks of the trade to how to graph rapidly and effectively using our knowledge or our base knowledge of different shapes of graphs. The specific objectives for this section are graph functions of the form y equals a times the function f of x, test for symmetry with respect to an axis, test for symmetry with respect to the origin, and graph translations of a function. Let's take a look at our first example. In our first example, we're going to go ahead and compare the graph g of x equals to 3 times the absolute value of x with the graph f of x equals the absolute value of x. Now, we've seen what the graph of absolute value of x looks like, and what we'd like to do is compare that to 3 times that graph. First thing we'll do is generate some tables of ordered pairs. When x is -2, g is 6. When x is -1, g is 3. When x is 0, g is 0, etc. We can see, of course, the rest of the numbers. And then we'll do the same thing for f. We'll go ahead and generate a table of ordered pairs for it. And that should look real familiar to us. We've done this one before. Now, if we're going to compare both those graphs, and we need to plot them simultaneously on the same coordinate system. So we'll go ahead and plot the graph of g, and then we'll go ahead and plot the graph of f. And the thing that we notice about these two graphs is that they have the same shape. It's just that the y values on g have been stretched. In fact, they've been stretched by a factor of 3. Let's go ahead and continue this example, and we'll compare the graph of g of x equal to 1/3 times the absolute value of x with the graph of f of x equals the absolute value of x. Again, let's generate a table of ordered pairs to plot. When x is -6, g is 2. When x is -3, g is 1, and so forth. Again, f of x, we know what the table of ordered pairs will look like on that function. And then we'll get ourselves out a coordinate grid, and we'll plot both of these graphs simultaneously. First, again, we'll plot the graph of g, and then we'll plot the graph of f. And this time, we notice that there has been a shrinking of the y values on g. In other words, the y values of g are 1/3 of what the y values were of f. Now, we've seen what that constant does when it's greater than 1 and less than 1 in front of the function f. Let's see what happens if we change the sign of that constant a next to f of x. Say, for example, we wanted to compare the following two graphs. F of x is equal to 1/3 the absolute value of x with the graph of g of x equals to -1/3 the absolute value of x. Well, if we plot f of x, we get a familiar looking curve. And if we plot g of x, we get, again, a familiar looking curve, but this time it looks as though it's been reflected, in fact, reflected about the axis x. What we know is that if we have this sort of reflection, is that if the ordered pair xy shows up on our original graph, then the ordered pair x -y will show up on our reflected graph. And that makes sense, because notice that what we've done between these two graphs is, in the first case, we have a positive constant times the function, and in the second case, we have a negative constant times the function, so that changes the sign of all of the y values. Now, let's go ahead and compare the graph of f of x is equal to the square root of 2x with the graph of g of x is equal to the square root of -2x. Again, we'll plot first our graph of f of x, and then on the same coordinate system, we'll plot our graph of g of x, making note, of course, first the domain of f has got to be greater than or equal to 0. That's why you're only seeing that one leg of the graph. And on g of x, we note that the domain of x has got to be less than or equal to 0, because notice all of the inputs into g have to be such that you're taking the square root of a positive quantity. So I'm going to need a negative x so that when I multiply it by the -2, I get a positive number. Now, another thing that we notice about this is that the graph of g appears to be the same exact shape as the graph of f, but this time we're reflected about the y-axis, or the graph of g is a reflection of f about the y-axis. Now, what that says is that whenever y shows up on the graph of f, the ordered pair -xy will show up on the graph of g. And if you notice between our two functions, what we've done is negated all of the inputs into g, and that's the difference between f and g. So we can generalize this whole idea of reflections about an axis by taking into account those two examples. We know that the reflection about an axis is going to occur in the following fashion. The graph of y equals the opposite of f of x is the same as the graph of y equals f of x reflected about the x-axis. the graph of y equals f of the opposite of x is the same as the graph of y equals f of x reflected about the y-axis. Now those are two very important concepts, and you should keep those in mind, and those should become top-of-the-head knowledge for you. Let's take a look at the following graph. The graph f of x equals x squared is symmetric with respect to the y-axis. This is a new concept. We're looking at some form of symmetry. All of us know a little bit about symmetry from our experience in the world, and we're going to try and see if we can define it mathematically. First of all, we'll go ahead and graph f of x equals x squared, and then we'll just observe some of the ordered pairs on f of x. We notice that whenever 1, 1 is on the graph of f, so is the ordered pair negative 1, 1. Whenever the point 2, 4 is on the graph of f, so is the point negative 2, 4. In general, we notice that whenever the ordered pair xy is on the graph, so is the ordered pair negative xy. Let's take a look at another example. Let's look at this time an example of symmetry with respect to the x-axis. The graph of x equals y squared is symmetric with respect to the x-axis. Let's go ahead and plot that graph. When we do that, again, we can observe some ordered pairs on the graph. In particular, let's take a look at the following. Whenever 1, 1 is on the graph, 1, negative 1 is on the graph. Whenever the ordered pair 4, 2 is on the graph, the ordered pair 4, negative 2 is on the graph. Or in general, whenever the ordered pair xy shows up on the graph of x equals y squared, so does x negative y. Now, what this does for us is it generalizes the whole idea of symmetry about the x-axis and the y-axis to some tests for symmetry. The graph of an equation is symmetric with respect to the y-axis if the replacement of x with negative x, in other words, we substitute in negative x for x, results in an equivalent equation. In other words, it gives us back the original equation we started with. Similarly, the graph of an equation is symmetric with respect to the x-axis if the replacement of y with negative y results in an equivalent equation. In other words, we end up back with where we started. Let's go ahead and take a look at some examples where we can use these tests. Let's say if we want to determine if the graph of y equals x squared minus 2 is symmetric with respect to the x-axis or the y-axis. Well, to test for symmetry with respect to the y-axis, it means to replace x with negative x. We're using the idea that we know when we're symmetric about the y-axis that the ordered pair xy and the ordered pair negative xy both will occur on the graph. So let's go ahead and do that. We'll take our original equation. We'll replace x with negative x. Notice that we carefully substituted in negative x using parentheses. That's very important. And then we go about simplifying the resulting equation. Now, since we ended up with the same equation that we started with, the graph is symmetric with respect to the y-axis. Now, if we were to test it about symmetry about the x-axis, then what that says is that we need to replace y with negative y. Doing that yields negative y equals x squared minus 2. And then we're going to go ahead and simplify or solve this equation again for y, which means multiply both sides by negative 1. And the resulting equation is y is equal to negative x squared plus 2, which is not the same as our original equation. Therefore, this equation is not symmetric with respect to the x-axis. Let's take a look at another type of symmetry, a symmetry that's referred to symmetric with respect to the origin. The graph of f of x equal to 1 over x is symmetric with respect to the origin. Let's go ahead and plot that graph and see what we mean by that. Well, if we notice, first off, if I take, for example, the ordered pair 1/4, 4, I also notice at the same time negative 1/4, negative 4 shows up on the graph. If I take the ordered pair 2, 1/2, I notice that simultaneously occurring is negative 2, negative 1/2. In other words, that whenever the ordered pair xy shows up on my graph of f, the ordered pair negative x, negative y will also show up on my graph if my graph is symmetric with respect to the origin. So that leads me to the tests for symmetry with respect to the origin. The graph of an equation is symmetric with respect to the origin if the replacement of both x with negative x and y with negative y results in an equivalent equation. Let's go ahead and do an example with this particular type of symmetry. Let's say we want to determine if the graph y equals x squared minus 2 is symmetric with respect to the origin. Well, to test for symmetry with respect to the origin, we're going to replace x with negative x and y with negative y. So we need to do both of those to do the test for symmetry about the origin. First, we'll go ahead and replace y with negative y, and then we'll replace x with negative x. And then we'll go ahead and simplify the resulting equation and see if it gives us back an equivalent equation. And we see that no, it doesn't. It gives us back y equals negative x squared plus 2, which is different than our original equation. So this graph is not symmetric with respect to the origin. Let's go ahead and do another example of symmetry about the origin. Let's try the graph x squared plus y squared equals 10. And we'll see again, is it symmetric with the x-axis, the y-axis, and the origin? So we'll investigate all three types of our symmetry on this one graph. Now, you guys go ahead and do that. Take a few minutes, and I'll be back with you. Okay. The graph was symmetric with respect to both axes in the origin. Hopefully you got that. Let's go ahead and show why that works. Well, first off, we'll go ahead and replace y with negative y. If we do that, we're checking for symmetry about the x-axis. When we do that, we get x squared plus the quantity negative y squared is equal to 10. When we simplify that, we get x squared plus y squared is equal to 10. We end up with an equivalent equation that we started with, so yes, it is symmetric about the x-axis. Now, let's go ahead and replace x with negative x. We're going to check for symmetry about the y-axis. When we do that, we get the quantity negative x squared plus y squared is equal to 10, which yields x squared plus y squared is equal to 10. So again, the graph is symmetric with respect to the y-axis. We've got that. Last but not least, we're going to go ahead and check for symmetry about the origin, which says replace x with negative x, y with negative y simultaneously. Simplifying this yields, again, the exact same equation that we started with. The graph is also symmetric with respect to the origin. Now, this should not surprise us much because hopefully we recognize that equation as being the graph of a circle. Okay, now the next topic we need to cover is about translations. How do we shift graphs around in the coordinate system? The first example we're going to look at is the graph of g of x equal to the absolute value of x minus 2, and we're going to compare that to the graph of f of x equals the absolute value of x. Now, we know what the graph of f of x equals the absolute value of x looks like, and what we're going to see is that the graph of g looks just like the graph of f, it's just that it's been shifted down 2 units. And what do we see? We see that the graph of g is the same shape as the graph of f, it's just been moved down 2 units. In fact, its origin was shifted down to the point 0, negative 2. Notice that f of x equaled the absolute value of x, origin was at 0, 0, and that point was slid down to 0, negative 2. Now, we can also do translations in a horizontal direction. Compare the graph of g of x equals the absolute value of x minus 3 with the graph f of x equals the absolute value of x. Again, we'll go ahead and plot the graph, our familiar graph, f of x equals absolute value of x first. And then upon plotting g of x, what we notice is that we moved the graph of f 3 units to the right. In other words, the graph of g of x is simply the same shape graph as f, it's just been translated 3 units to the right, which means that the point that was playing the origin is now no longer at 0, 0, but at 3, 0. And it's now symmetric about the line x equals 3 instead of symmetric to the y-axis. Now, one more time, this time we're going to take a look at graphing g of x equal to the absolute value of x plus 1 plus 2, and we're going to do that using translations of the original graph f of x equals absolute value of x. So our first step, of course, is to plot f of x. Then we take advantage of our horizontal shift, which we've moved 1 unit to the left. And then we'll take advantage of our vertical shift, which means go up 2. And we notice that our origin point is moved from 0, 0 to negative 1, 2, but the graph has the exact same shape. So let's combine our work with translations that we've just completed with our previous work on stretches and shrinks. Let's take a look at the following example. Let's say we're asked to graph the graph of h of x equals the absolute value of 3x plus 3. Well, first off, we notice that there's a common factor of 3 in there, so we're going to go ahead and factor that out. And then we're going to use our properties of absolute value to bring that 3 into its own absolute value. And then we know the absolute value of 3 is simply 3. So that tells us that h of x is equal to 3 times the absolute value of x plus 1. So what that tells us is that we have a stretch of 3 units on all of our y values, and that we have a horizontal translation over to the point -1. So, to graph h of x equals the absolute value of 3x plus 3, we will translate and stretch f of x equals the absolute value of x. So, we'll go ahead and graph this stepwise. First of all, we'll go ahead and graph f of x equals absolute value of x. That's our reference graph, so we know what the general shape is. Then we'll go ahead and do the translation, shift it 1 unit to the left. And then we'll go ahead and do the stretch. In other words, increase each of the y values by a factor of 3. And that gives us the resulting graph. Okay, let's take all of these ideas that we've been talking about in terms of translations and put them in a chart so we can kind of summarize how to translate a graph. The first thing we know is that if I have a graph y equals f of x plus some constant, we're going to shift the graph of y equals f of x, that basic shape that we already know, by c units. And in the case of where we're adding a constant, if that constant is a positive constant that's being added, we're moving it upward. If y is equal to f of x minus c, then we're going to move that graph, that basic shape of f, c units downward. If y is equal to f of x plus c, then we're going to shift that graph c units to the left. And if y is equal to f of x minus c, we're going to shift that graph c units to the right. Let's go back to this chart one more time. What that says is on the first one is that our new origin point is now going to be at the point 0c. On the second one, our new origin point will be at 0, negative c. On the third one, our new origin point will be at negative c0. And on our last one, the new origin point will reside at c0. Well, we've covered quite a bit of information on this tape, and one of the best things to do with this material is to get out there and do a lot of graphs, and you'll get the hang of how things move around. And it actually turns out to be kind of fun once you get going with it. So go have a good time with it.